Okay.
Perfect. So good morning, everyone. For those of you that don't know me, my name is Solango. I served as a vice chair of this section for this past year. And so now that we're at the end of our 2023-2024 season, we just want to say thank you to all of our members for a very successful year. We did take that plunge back did mix it up. Highlights last tour in Burlington for Czech. That was very well attended. Thanks again to WearCheck for hosting us. And then also a huge thanks to Connectric for allowing us to use their facility quite a few times, including for our very successful Education Day seminar that happened last month. So again, just a big thank you to the sponsors. And just so you know, we're always happy to sign on more sponsors because the money does go a long way, and it's for a good purpose. It supports all the events that we do, and as well as various events that we hold at high have and events have to do with tribology. Thank you so much. Please reach any one of the that you're locally prominently. The other thing I did want to say is that, the section runs because of the hard work of volunteers. And so we're always welcoming people who are willing to volunteer their time to, whether it's in an effort to increase membership or to help out with our website. There's different things that we're needing help with on an ongoing basis. So once we get started back up in September, it would be good to have some fresh blood volunteering with us. And so, yeah, again, do reach out to myself, Payman, or Jim, or anyone on the board if you'd like to help out that way. And then finally, just a quick announcement for those of you in the Toronto area, we will have our final in-person get together on April 30th, which is next Tuesday. And we're going to meet at a location that will allow us to just network in a relaxed atmosphere. So play some pool, some ping pong, and enjoy some refreshments. And so check your email for that. That's as a thank you to our members. And if you're headed to the annual meeting in, I guess, next month, have a blast. I myself won't be able to make it this year, but it's always a really good annual meeting. And so with that said, we will see you all in September again. Thank you.
Okay, so we're going to continue over to our presentation now, Solango. Anything else?
That's it on my end. I think you can go ahead and introduce Stephen, please.
Okay, thanks, Solango. Good morning, everyone. My name is Jim Ryan. I'm a retired past chair, past education, past everything on this thing. Yen Garcia is not here today, so he's asked me to introduce our speaker. So Stephen Marshall is our speaker today. He comes from Rechochem, and so he is going to be talking about engine coolants. And I hope Stephen notices I call it a coolant, not antifreeze. Quite often I would be doing presentations and I would be talking about antifreeze, and my American colleagues say, Jim, it's a coolant, it's not an antifreeze. Well, for us in Canada, we call it antifreeze. Anyway, Stephen has his engineering degree from the University of Alberta. He continued on and got his master's, and it's the master's in industrial automation engineering. So is that also at U of A?
No, that was from a university in Australia. So, and now, like typical engineering, now I don't do any automation or anything. So,
oh my gosh. Anyway, Stephen's been around for a little while at Rechochem, and he brings a wealth of knowledge and passion to the industry. And with that, I'd like to turn this presentation over to Stephen to talk about the thermal management fluids.
Okay, thank you very much, Jim, for that wonderful introduction. Yeah, so as you said, my name is Stephen Marshall, and I work at Rechochem. Officially, I work in technical service, and that means that basically I just solve people's problems, basically. Yeah. So today we are going to talk about some antifreeze or coolant, depending on where you're from. So yeah. So before we start, I just wanted to say that if anybody has any questions as we're going on, feel free to ask as we go along. And if it gets to be too many, then we'll postpone it to the end. Of course, there will be an opportunity to ask questions at the end as well. So there we go. Um, so for today's agenda, we're going to be talking about antifreeze basics, and that will just include like composition of antifreeze, the general purpose of antifreeze, what the function is. Then we'll talk about coolant types, as there's a few different types that we should be aware of. We'll talk about some coolant system issues such as cavitation or scaling or other issues that commonly come up, and we'll discuss what we should do to prevent them. And after the issues came up, we'll discuss what needs to be done to fix that as well. We'll talk about coolant maintenance, which is a fairly important topic. And lastly, we'll talk about analytical testing. And so when I'm speaking about these topics, the antifreeze basics will be just purely based on science, but as we get deeper into the presentation, it'll become more and more what we recommend that companies do for their thing. So it'll definitely have like a perspective from my company, but in general, we consider it to be good. Some companies may have differing opinions. Okay, so without any further ado, let's talk about our antifreeze coolant basics. Um, so the function of coolants. So the primary function of coolants is to transfer heat from point A to point B. And this is true for all heat transfer fluids, and engine coolants are just a type of heat transfer coolant. The secondary function for car engine coolants is to provide freeze and boiling protection. So one of the issues that you face, of course, is if you live in a colder climate, that your engine coolant will freeze. And of course, when it freezes, it bursts and cause a bunch of different issues. But it should be noted that in some countries where they don't receive freezing temperature, they're not concerned about this particular function of engine coolants. So they can have a different product designed for them. Unfortunately, whenever you run a coolant through an engine, there's always a lot of corrosion. So you need to come up with a way to prevent the corrosion from happening. So these are the three main functions of engine coolants that we use today, especially in North America. Okay, so in a coolant, it's just like baking a cake in the sense that a cake has certain ingredients that are almost always present. And you can have like different styles of cake, but they'll always have eggs, they'll always have flour, or at least an egg substitute. So when we talk about coolants, I think it's helpful to look at that in the same way. So in general, for coolants, the first ingredient that we have is quality water. And it's important that we use quality water. And of course, when I tell my poor wife about this, she says, well, water is water, but that's actually not true. It depends a lot on what's dissolved in the water. So whenever you use an engine coolant, you should be using a distilled water that meets the ASTM spec. Next, we will use glycol. And again, we have to use glycol that meets the ASTM spec, and it's mostly just a purity spec. And then lastly, we add the corrosion inhibitor package, and as well as anti-foam, dye, scale as well, or scale inhibitors. And this is the producer's technology, and this is where companies can really compete with each other and where the competitiveness in this comes from. Because all the companies want to solve all the problems that we outlined earlier, and they do it by coming up with different corrosion inhibitor packages, and that's why we have different brands on the market. And when you put them all together, that's how you get the antifreeze or your coolant. So I would like to look at each one of these parts more closely now. So the first one that we should look at is we should look at the heat transfer medium. And in our engines, we use water. But in other heat transfer applications, you don't necessarily have to use water. Um, for example, some will use molten salt to transfer heat as a more extreme case. So for water, the reason why we like water so much is because it has a high heat transfer capability. So this means that it's able to move the heat from point A to point B the most effectively. Um, at least the most effectively of the materials that are readily available and cheap. Of course, as we all know, price is an important part. So we don't necessarily go for the absolute best uh, solution, but we go for the best solution within our price. One of the downsides of water is that it freezes at 0 degrees Celsius, as well as corroding the system. And as we speak about before, high quality water must be used. One of the issues that we commonly see is that people will buy a concentrate. We'll get into exactly what a concentrate is later, and then they will mix in their own water, and they'll either use the wrong kind of water or they'll won't mix it properly. So that's why we often try to sell pre-diluted coolant, um, just to avoid those issues. So for the water quality, as per ASTM D3306, and ASTM D3306 is kind of the big standard that all coolant manufacturers try to get to. It has a series of tests that you have to complete before you can claim that it's a coolant according to the standard, and it's the one that at least we use for all of our coolant. So the best sources for the water is reverse osmosis water, or deionized water, or distilled water. Problem sources are well water, rainwater, and tap water. So, and of course, this is just an example of some scaling that can happen. This is obviously not in an engine, but just to show what can happen. Oh yes, and boiled water. I had a complaint about somebody. Somebody had a complaint about our product, and it turned out that they were boiling their water and then using that. And of course, that doesn't get rid of any of the minerals at all. So when we talk about how pure we want the water to be, on the left here, I have like for the drinking water hardness that the WHO says that we should be using. So for them to be soft, for drinking water, we're looking at about less than 60 milligrams per liter. But when we're doing our coolant, we're looking at 20 milligrams per liter. So it's about 3 times less hard than drinking water. So, and this makes sense because we don't have filters in our cooling system to get the water. So, yeah. Okay. So the next major component in a coolant is what I call a base. And the two bases that we use are basically ethylene glycol and propylene glycol. So, and it has a couple functions in it. The first function is that it raises the boiling point a little bit, yeah. And the main reason why we use it is it lowers the freeze point. So the difference between EG or PG is ethylene glycol is the most effective, but it's also the most toxic. So in some situations, you wouldn't want to necessarily use EG. For example, if you have a cooling loop for a ice cream facility, uh, for an ice cream freezer, then you wouldn't want to have one because if it leaked, it would get into the ice cream and then it would cause some issues. So there, they would probably more likely to use propylene glycol. But propylene glycol is more expensive, but the big upside is that it's non-toxic. In 95% of applications that we see, at least for engine coolants, is with EG as well, though. Yeah. Okay. And next, we have our additive package. So this additive package has a bunch of normal things that are there in the usual formula. This can vary depending on the exact brand that you're buying or the exact product you're buying. So in the usual formula, they'll try to protect against liner pitting. This will be used in heavy duty applications, but not in light duty applications. It'll protect against scaling. Um, Typically, it's better to use proper water than to put in an inhibitor to protect scaling. The issue is that adding, well, it just costs more money to keep adding more and more stuff in. Okay, uh, protecting against corrosion, this would be in every single heat transfer fluid or every single engine coolant that we have. And to protect against cavitation, that'll be in heavy duty. And to protect in changes in pH. So if your pH goes too low, your engine coolant will attack the ferrous metals. And if it goes too high, it'll attack aluminum. So it's important that in your engine coolant, you have something to buffer it. So that way, if there's a little bit of acidity being added, it'll eat up the buffer instead of lowering the pH. And that's an important part. Okay, when we look at the inhibitors, um, there's actually a lot of inhibitors that we can add, so this is not a complete list, but I just thought this was a good example. So on the left, we have our inorganics. So we have nitrate, silicate, molybdate, phosphate, and borate. And on the right, we have our organic acids. So those are benzoate salts, carboxylates, and azoles. And there is a difference between them. So we divide engine coolants into what we call IAT, which is inorganic acid technology. And this uses the inorganic acids from the left here. And then we divide it into the OAT, which is organic acid technology, and that will use what's on the right. And of course, you can mix them as well. So, and basically what we're looking for when we do inorganic, when we do put our inhibitors in, these are some of the inhibitors and what they do. So I won't go through them all, but one of the ones that's most important, at least for heavy duty applications, is the nitrite, which people use for iron to protect against that cavitation. And you don't need nitrite, and we have nitrite-free coolants. There's a lot of nitrite-free coolants on the board, but this is one that a lot of clients will be looking for. That's important. Yeah. Okay, so now I want to go over the difference between the conventional and organic acids. So generally, the way how inhibitors work is in conventional methods. Actually, I think I can go here. Yeah. So on the left-hand side, the little squares are the conventional, the inorganic technology. And what they do is they form a very thin layer on the inside of your system. And then what happens is it gets corroded instead of uh, the actual metal. The downside with this is that it gets used up. So you need to be replacing your engine coolant a lot faster as the inhibitors get used. On the organic side, which is on the right, the inhibitors will stay inside of the fluid and they will react to the spots and then they will come back into the fluid. And from a scientific perspective, we're not 100% sure exactly how it happens. Although we do have there is good research on it, but there's still some questions on that. So if anybody's looking for a thesis to do for a PhD, this would be a great topic to work on. Okay, so yeah, so in the conventional, there's a chemical reaction where your nitrate will convert or will react with the chemical. In the organic acid, it's adsorption, which means that it just stays on the outside. And as I said before, the conventional one, there's some depletion. And then for the organic one, uh, they mostly do not deplete. Of course, over very long intervals, there will be some degradation of the organic acids, but they can last for a very long time under normal conditions. Oh yeah. And then for site selectivity, the conventional, they don't pick, I guess choose, they don't actively adsorb on the sites. They are just everywhere. So, and the organic acids work better. So in history, the inorganic acids were developed first. And so a lot of engines, especially in the 90s and maybe early 2000s, you can see that they recommend using conventional. But generally, we try to recommend that you use organic acids because they're better for your system and they can be more cost effective because last longer. Okay, so I just wanted to look a little bit at the what happens with the corrosion inside of the engine. So we have a test that's called ASTM D1384, and it's a pretty simple test. So what you have is you'll have 6 different metals: copper, solder, brass, steel, cast iron, and cast aluminum. And you'll have them in a little bundle. You'll stick them in a beaker. You'll put your coolant in that beaker. You'll add some oxygen to it, and you'll add heat. And then after 2 weeks of sitting in that mixture, you take it out and you measure the weight loss. So the more weight loss that's happened, the more corrosion there is. And it's not if you pass this test, it's more of a benchmark test just to say like you're ready to go on to further screening. So what I wanted to say though is if we just use water, we get some pretty strong corrosion, especially in the cast iron and the mild steel. And I mean, of course, this makes sense. I think people intuitively know that. When we just put ethylene glycol in, then what happens is it attacks the solder and the mild steel and the cast iron. Usually for this test, you're looking for numbers less than 10, except for aluminum and solder where you're looking for 30, less than 30. So if you just put water or EG in, it fails completely and you never use it. But if we use inhibited EG, then we see that everything actually passes. And you can see that there's a negative loss onto the aluminum. And that just means that part of the EG reacted with the aluminum to give it some extra weight. But it's such a small number for aluminum that we never actually worry about it. And for aluminum, it has to be less than 30. So this shows that when you inhibit your ethylene glycol, that it's very important and we need to be doing that. Okay, so one of the next questions I always get is about dye. So dye has no effect on the performance of the engine coolant. And this is a guideline that was created by TMC for the color of your coolant, except that nobody follows it. So just because you're using a red engine coolant in your truck or your car does not mean that you can put another red coolant in and they're equivalent. So yeah, unfortunately, the purpose of dye is, in my opinion, mostly marketing, but also it does help with leak detection and yeah. So yeah, never mix the dyes just based on dyes. You need to see how it's actually formulated. Yeah. Okay, so for here, I want to talk about concentrate, premix, and water base. So when we're making coolants, you can generally have a concentrate, which you won't put in your engine. You'll have to dilute it down. You'll have a premix, which is designed to be sold at that particular uh, mixture, and then you'll have water based where we don't put glycol in at all, and that can be used for various purposes. For example, train engines don't use any glycol because they heat the train engine prior to starting it. So when we're looking at the amount of additive package, in the concentrate, you have a higher percentage of additive package. And that's because when you add the water, it gets diluted down to the proper amount. So in the premix, you'll have the proper amount. And you have to be careful when you're doing your concentrate um, because concentrates are typically set up for being diluted down to 50-50. So if you decided that you wanted to put, say, 20% concentrate and 80% water in, you'll be diluting the inhibitor package quite substantially, so you might not get protection with it. So it's important that from whichever coolant manufacturer you get your uh, engine coolant from, that you're following the guidelines on how much water you can add to it for the concentrate. So yeah. Okay. And even in the concentrate, there's a little bit of water. This is usually done to help with solubility, um, because water is better at dissolving than your glycol is. And also, yeah, we'll talk about it in a sec. And then the rest will be the either PG or EG. So yeah, and one key note is when they say it's a 50-50 mixture, it's actually not like 50% water and 50% glycol because of the extra bit of additives that are added in, and because there's water in the concentrate as well. So yeah, but when we do our information for everything, we call it 50-50, even though it's not actually, but yeah. Okay, so I just wanted to take a look at the thermal conductivity for the mixture. So when we're looking at, for example, water versus a 50% EG in water, at 20 degrees Celsius, you can see that you're going from about a 0.6 to about a 0.39. So you're losing a fair bit of thermal conductivity when you're adding the EG. And this is compensated for by engine design by having in the cooling system, you design it for using EG and water. But it's actually quite substantial, and that's why if you don't need to use EG, you probably shouldn't use EG. And then you see a similar result when you look at the thermal conductivity at 100 degrees Celsius as well. So when we're looking at the boiling point, um, under atmospheric pressure, you can see that you gain some boiling point. I actually can't remember the exact number, but I believe it's about 8 Celsius that you gain on it. But the thing is, when we put an engine coolant into the engine, it's a closed system. So as it heats up, it builds pressure. And with the pressure, the boiling point actually goes higher. So that's why you can have an engine running hotter than 110 degrees Celsius and it won't be boiling the engine coolant because of the pressure. Okay. And then for freeze point, um, so when I started here, I didn't realize the freezing curve looked like this. So on the left-hand side, we have 100% water, and on the right-hand side, we have 100% EG concentration. So as we add more and more EG into the system, we see a depression in the freezing point. And so at 50-50, we see minus 37 degrees Celsius, and this is good for most applications. But if you work up north, sometimes you need more than that. So at about, I believe it's 69.31, you'll see a minus 64 degrees Celsius freezing curve. And this is as good as you can get. Once you start going past that, you actually lose your freezing point depression and it begins to return back to normal. And this is why, this is another reason why in concentrate, why we add water. Because when we ship, if you just put it in EG and say you could get your additives to dissolve in it and you shipped it, sometimes when you ship it, it goes lower than 0 degrees. And so you can actually freeze your concentrate when you ship it. So we add a little bit of water into it to make sure that you're still getting some freezing point protection. Yeah. And it's important to note that, yeah, there's almost no reason to put in, like, for example, 80% ethylene glycol and 20% water, because not only are you reducing your thermal conductivity and your heat transfer properties, you're also making it more viscous, and the freezing curve is not as good as it would be if you did 70-30. Yeah. So, and then for boiling, the boiling curve looks fairly normal, where it just goes up. So yeah, there you are. Okay, so for this one, I want to just talk a little bit about the specifics of how what do I want this? Yeah, of how a engine coolant system works. So there's actually two loops in an engine for the cooling system. There's the main loop and the bypass loop. And I'll explain that right now. So when the engine is cold, you don't want to lose heat in the fluid. So you don't run it through the radiator. The radiator is on the right here. What you actually do is you run it up, it cools off the engine, and then it comes back through this water pump here, and it takes the bypass back, and it just does a loop that never goes through the radiator. As it gets hotter and hotter, the thermostat, which is right here, it'll open up, and it opens up progressively, and it will start to let some engine coolant into the radiator and then coming back. And this was the way how you can keep your engine warm to a certain degrees. And usually what we're looking at for engines, it depends really on the generation of the engine, but about 90, 88, 95 degrees Celsius is what we're looking at to hold the temperature at. And yeah, I mean, this can vary a fair bit. So the important thing to remember is there's two loops, one that goes through the radiator when it's warm, and one that goes through the bypass when it's cool. Okay, and just as a quick review for what we talked about in coolant basics is when we're making engine coolants, the thing that we care most about is thermal management. And this will be the engine parts. So that'll be block, liners, cylinder head, of course. But also there's oil coolers that they can use the engine coolant to manage the lubricant's temperature. And then we can have air and def because diesel exhaust fluid, for example, freezes. So some of the equipment will have a coolant loop that goes to the diesel exhaust fluid to heat it up. So there. The second function is to prevent freeze up and boil over. And we need to be providing corrosion protection. And we need to provide cavitation protection as well. And we prevent against scaling. And we have to make sure it's compatible with hoses, elastomers, and seals. And we need chemical stability. So one of the issues with one of the chemicals that we don't recommend people use is 2-EHA because it's a plasticizer of certain kinds of hoses and elastomers and seals. So if you do use 2-EHA, which you can do, you need to make sure that when you're buying a new seal or a new gasket or a new hose, that it is compatible with that 2-EHA. Sometimes you see issues where the people don't buy an OEM seal and they put the wrong one in, and then there can be issues. Okay, so that sums up our coolant basics. Next, I want to talk about some common coolant system issues. So what we're looking for is failure type. So one of the most common issues, at least with heavy duty, is wet sleeve cavitation. So here's a picture of wet sleeve cavitation. And I'll just go over quickly in my own words what cavitation is. So basically, in a heavy duty engine, you have a liner, and the liner is right where the piston goes through. And the piston goes through pretty fast. So the liner vibrates back and forth, and the water right on the edge of the liner, it gets pushed away. And then when the liner gets pulled back, the water doesn't have enough time to catch up to it. So what happens is you create a small amount of vacuum. So, which this says bubble, but a bubble like typically has something in it. So it's not, yeah, you have a vacuum. And then with all that pressure, the vacuum collapses and it dissipates the energy on the cylinder wall. And eventually the corrosion and the pitting will occur. So this is a major problem for it. And when we're putting inhibitors in, we always are considering which inhibitors to put in for cavitation. Okay, so yeah, so this is a picture of it. And again, this is an extreme case of it, but you can see that it's already gone through half of the cylinder wall, and it's a major issue. And so in general, unfortunately, if you have cavitation, the general solution is you have to pull up that liner and you have to put a new one in. There's no like patchwork or anything of that sort to do it. And yeah, nitrite is a common inhibitor to protect against wet sleeve cavitation, but you have to be a little careful with your nitrite because if you put too much in, it attacks aluminum. And that is like the crux of the issue with chemistry is you have to put in certain chemical, you put in too much that causes this problem. So then you put in chemical C to compensate for that, and then that causes problems. So it takes some effort to balance it out. Okay, the next failure type is oat deposits. So that's organic acid technology, and it looks like this. This will usually happen if you have too much OAT inhibitor. So if you add a concentrate, direct concentrate to your engine, you will have way too much inhibitors because we're expecting you to be diluting it by 50% or between 40 and 60%. So if this happens, you need to rebalance the formula, which unfortunately typically means draining out the engine coolant and putting the proper coolant in as well. Another cause for OAT deposits, which I don't have written here, is if you put too much heat into it. Sometimes you can, it'll cause the OATs to precipitate out and then they burn to the side of the liner. Yeah. Okay. And now for an interesting one is for cab flux incompatible coolant. So yeah, cab flux. Okay, it's a bit of a story, but that's okay. Um, so if you just have iron sitting on your table and you let it sit, it will constantly oxidize and it'll be destroyed. So that's bad. For aluminum, though, if you stick aluminum on a table and you let it sit for 1,000 years, it will stay the same. And that's because aluminum does react with the oxygen, but it makes an outside layer of aluminum oxide. And this is really good for preserving aluminum and why it doesn't rust, and it's good. Unfortunately, that layer on the outside, when you're welding, it doesn't weld together. So what people do when they're making radiators is they put a flux on top of the aluminum, and it removes that oxide layer, and then they'll weld it together, and then they can get a good weld. Unfortunately, sometimes they leave that flux on top of the engine, or on top of the radiator, and then when you have a coolant that goes through it, what happens is it washes away that flux, but underneath the flux it's not the aluminum oxide layer anymore, it's just the aluminum. And sometimes the engine coolant will attack the unpacified aluminum. So when we design, or when people design their engine coolants, they have to take this into consideration. Generally, radiator manufacturers try to remove the flux by flushing it, and it is pretty dissolvable in water, so that works. But if you don't, it can cause issues. And so the best way to combat this is to flush out your radiator first, but then also just make sure that the coolant you're using is compatible with the cab flux. So, yeah. Okay, the next failure type I want to talk about is pump cavitation. So this is cavitation again, and it's the same idea. As the pump spins, the water can't catch up to the pump, the fins, and then it makes a little vacuum bubbles and then explodes. So yeah. So this is cavitation in the pump, and again, you have to be making sure you're using proper coolant. If you don't, then you'll have to replace the pump. It's the only option. Okay, and then now if you see coolant deposits on the radiator cover, then you might have used SCA, which is in for conventional fluids. If you run out of inhibitor, what you can do is you can get a little package and you can dump it in and it'll rebalance it out. So the way to get rid of it is to rebalance the SCA or to change to a different coolant. So typically the SCA issue only happens with the conventional coolants. So if you switch to an OAT, then you're pretty happy. Okay, so for scaling, um, scaling what it does is it creates a little layer on the metal surface like this, and it acts as an insulator. So what that means is that there's not as good a heat transfer anymore. And scale from hard water forms an insulating layer on the surface of the metals. Heat transfer is reduced to such a degree that 1.6 mils of buildup is like trying to transfer the same amount of energy through 114 mils of cast iron. So this is one of the bigger issues that we face from time to time. And the real issue with this is that it doesn't do damage fast enough. So my father-in-law is a farmer, and he always just uses well water, despite what I tell him. And the issue is he says, "Well, I've been doing it for 10 years on this truck or this tractor, and I haven't had an issue." The problem is that it reduces the lifespan of the vehicle. So it's like, yeah, you did do it for 10 years and it worked out fine, but if you didn't do it, then you might have gotten an extra 3 or 4 years out of the vehicle. So we really, really stress that you want to avoid using well water and you want to use high quality water. Okay, so next we're going to be looking at some coolant maintenance for this. And so there's estimates that 40 to 50% of heavy duty engine failures can be traced back to problems in the cooling system. Yeah. And the way how at least we classify it is we classify engine issues into system problems, which would be like part related or contamination, and then fluid problems. And they're related to each other. Typically, when you have a fluid problem, for example, your inhibitor depleted, it'll cause a system problem. So yeah. Um, so when we do maintenance, typically people don't want to do maintenance because it costs money, it costs time, there's a cost of the coolant, the new part costs, and there's a bunch of reasons why we're not to don't want to. So we get a lot of availability uh, costs as well. Okay, but what they don't say is that there's a cost with failures as well. So we need to be trying to balance these two things. And my thingy's not. Here we go. So when we talk about maintenance, there's generally four different types of maintenance. So there's reactive maintenance, which you fix after a complete failure. Corrective maintenance, where you fix after the problem has accrued. Preventative maintenance, and then predictive maintenance. Typically, we recommend people to do preventative maintenance on their vehicles, um, which is the idea that you want to be taking some samples from the engine coolant at a set period and testing that, and then we can check and see what the inhibitor levels are. Are we seeing any corrosion inside the fluid, whatnot? Of course, we do not recommend reactive maintenance where you have a complete failure, but it does feel that most people are more on the corrective maintenance. Um, so when we talk about doing corrective maintenance versus preventative maintenance, if you just do preventative maintenance, so this would be the overall lifetime of a part, where the part performs well until a certain point and then it fails. Unfortunately, if you have an issue, you can cut that graph down where the part life will fail faster. So if you're constantly monitoring it, then you can fix it. So yeah, we call this, yeah, so that's basically the idea behind this. So when we talk about the intervals for when to do your maintenance, so CK4 is an oil, like a lubricant. So they recommend, the DDC recommends that you replace your oil every 75,000 miles or 121,000 kilometers. With engine coolant, for our SLC, what we recommend is you do a maintenance interval every 121,000 kilometers or 1 year. But that doesn't mean that you have to drain it. It means just to see what is inside of the engine coolant to check for corrosion and the stability of the fluid life. And then we usually recommend doing a drain interval every 300,000 miles or 480,000 kilometers or 2 years. With our extended life coolant, which is our OAT, we recommend that you do a maintenance interval every 150,000 miles or 1 year, and we recommend you do a drain every 60,000, 600,000, miles. And so when we're trying to push people to go into the organic technology, um, when you are draining your engine, there's a downtime on your engine. So the less you have to do that drain, the better off you'll be. So that's why we recommend doing the longer fluid. Yeah. Okay. So when you're doing your coolant check, there's stuff you can do just by yourself without needing to send it to any analytical lab or any anything like that. And so one of the best ones you can do is you can just use a refractometer to see the freeze point. And this will show any glycolic degradation or any issues you have there. The next one is those strips, the AccuStrips or whichever strip brand you prefer, will measure the pH. It can measure other stuff as well, but we found them to be not completely accurate in that sense. It's good for a just a general overview, but you would never want to make like a major decision based on it. You would put it in, and if it said that X inhibitor was low, you'd probably want to send it to a lab for an annual for a test. Okay. Um, so you can do the field testing by yourself, and then we usually recommend that you send it out for testing to a lab. So when we look at analytical testing for labs, one of the most important things that you should be looking for in a lab is ISO 17025, and this is an accreditation for the lab, and it shows that we're doing everything according to a standard. We have methods to ensure the validity of test results. There's a results approval process. There's a auditing process. There's equipment maintenance, and it's really, I feel that it's really important that the whichever lab you'd go to has this. So when we're looking at the actual lab equipment, and I won't go into super detail here, we're looking for things like the HPLC, which stands for high pressure liquid chromatology. It detects HPLC, or it detects nitrite and nitrate and your organic corrosion inhibitors. So this will be used to determine basically your OAT. Yeah. Another machine that people commonly use is ICP, and ICP detects metals and contaminants, corrosions, and others. Um, so this test method is really good to get if you're concerned about corrosion because you can see how much elemental metal is inside the fluid. So for example, if you found that, say, you had 300 parts per million of iron or zinc, you would know that you're having some corrosion or some issue there. So yeah. Um, Okay, and for IC, which is another type, what you can test is you can test out some anions. So this is good for testing out inhibitor levels. Yeah, and then for freezing point tests, so one of the issues with the refractometers is the refractometers are very good for field test things, but they only work if you have a clean sample. Because it's based on the way how light bends in the fluid. With two fluids, you can determine what the freeze point will be. But if there's any contamination or anything like that, and it becomes three fluids, then you can't. So it's good to have a lab level, an analytical level uh, equipment to determine what your freeze point would be. And freeze point is pretty important. Okay, so and there's also a lot of other analytical lab. I work in the lab, so I quite enjoy talking about this, but I was told by my friend that I shouldn't talk about it too much. So I'll just leave that there. And I think that we have about 8 more minutes left or so before the end of the meeting. So I just wanted to thank everybody for their attention. And if there's any questions that people have, either feel free to contact me at smarshall@Rechochem. And if you have any questions now, um, I'm available to answer some questions for you guys.
Any questions for Stephen? You did a very good job covering all the basics here. Everybody pretty well fully up to speed.
Yeah.
Hi, sorry about that. I was wondering if you could talk a little bit about compatibility, moving a customer from product A to
Oh, yeah.
product B.
Yeah, so I don't know why we don't. I need to put compatibility in this because this question always comes up. So yeah, give me a sec here and I'll go back. Um, so yeah, with products, it depends on the actual product. What am I looking for here? These ones. So in general, what we say is we say that you can mix like packages. So the best thing to do if you want to be 100% safe is just don't mix. The next best thing to do is to talk to your manufacturer for what you should be able to mix. Because you see people mixing things and it does cause issues because it throws the inhibitors out of balance. Generally, what we say, very generally, and there's even risk here, is that if you have the same inorganic chemicals inside of it, then it's okay to mix. But the issue is that if you have different brands, like if you have our brand and cat, we put different amounts of, like, say, phosphate in it, for example. So when you mix them, you change that proportion. So that's the issue. For our company, we do a lot of compatibility between different products. So when we've done that compatibility, we will say like it's okay to mix. And like we have a product that we've specifically designed to just mix with anything. So, but I'm not sure what other companies do for that. So yeah, so sorry, my answer is basically don't mix unless if you absolutely have to. If you do have to, contact your manufacturer about it.
Thank you. And by don't mix, do you mean like a flush or do you mean a drain
Oh,
and fill is sufficient?
oh, sorry, there's two different kinds of compatibility. And in the lab, usually when we think of compatibility, we think of like if you go 50% Rechochem and 50% Cat. Um, for uh, for the other kind of compatibility, which is like what kind of engine coolant can you use inside of an engine, uh, we like always follow what the OEM says. So, for example, Picard will say that they want you to use a nitrite inhibited engine or a nitrite inhibited coolant. So if they say that, then that's what you should do. Um, Past that, like you really just need to contact the manufacturer of it, of the engine coolant, and then they'll have the details about what specific engine they can use or we can use for it. And so when you are doing, yeah, because everybody what they want to do is when they switch coolants is they just want to top up with a new coolant for it. And that's where like the lab version of compatibility comes in, and you need to be very careful when you do that. And sometimes it'll be okay when it's like 20% of cat and 80% Rechochem. But then as you go up and it's 40% cat and 60% Rechochem, then suddenly you'll have an issue. So you just have to be very careful with it. And the best thing is to contact the manufacturer. Does that answer your question?
Yes, thank you.
Thanks, Stephen. Any other questions for Stephen?
And I just want to add one more thing. Like we do recommend usually a flush and fill, which would mean that uh, what you do is you empty it, you run water through it or the new engine coolant through it, and then empty that and then fill it up with the new stuff. And this is the best way that makes sure that your engine coolant inside of your engine is as close to the recommended values as possible.
Hello.
Hey,
Hi, sorry. I'm in the car with a bad reception. If you said that and I missed it, I apologize. But my question is, when you test the coolant, how about the haziness? Does it tell us something about the remaining life on the coolant or no?
so for haziness, we have a method that will look at like the appearance of an engine coolant. And so we use that when we're going with it. Generally, we recommend if there's haziness, generally you have an issue. So, like, if you have haziness, the best thing to do would be to send it to a lab, have the lab analyze it, and then go on what the lab recommends for it.
Okay, thanks.
Yeah, yeah. And so one other thing with haziness is sometimes when the ethylene glycol or the PG or the propylene glycol gets really old, sometimes the haziness will appear. And so it's a little bit risky because there'll be degradation with it as well. So yeah, haziness is not great, but sometimes you can make it work if you are really trying to pinch your pennies.
So the source is the degradation of the glycol, or there are different sources
Oh,
contributing to the haziness?
there's so many things that can cause it that, like, that's just one point, is the oldness of the glycol. Yeah.
Okay, thank you.
Very good. Stephen, I just have one question for you. Do you have any market input, like what percentage of the market is converted over to the organic acid technology, which is probably the last 20 years been around?
Yeah, I actually don't have any information on
You
that.
don't have, okay.
Like, I'm totally on the technical side, and I do branch out to talk to the more business side of things. But yeah, I have honestly, I have no idea.
Okay. Well, thanks very much, Stephen, for an excellent presentation. We had some interesting questions there. Thanks, Bashad and Andrea. If by all means, if you have any more questions, you can pass them into our committee, and we can always get back to Stephen and ask him for further clarification as well. Payman has recorded the session, so I think it will be available through our website sometime later for you to review this presentation once again. So, Solongo, if you have any closing questions or comments, I'll pass it over to you.
Thanks, Jim. I just wanted to say thanks again to Stephen. We enjoyed that. And in terms of closing remarks, just thanks again for a wonderful year here at the Toronto section. I hope everyone has an amazing summer and September. I'm happy to be serving as chair again in September after I think a 10-year break of doing that. So looking forward to seeing you all in September. And those of you in the Toronto area, we'll see you next Tuesday at JJQ's for our social networking event. Thank you so much and have a great day.
Bye, everyone.
Thank you, everybody. Enjoy the rest of your day.
Thank you.
So thanks, Stephen, for all your help. Really appreciate your support.
Yep, no problem at all.